Welcome to the arithmetic zone, and welcome to our part 2 of partial fractions. So in the last part of partial fractions, we covered how we can decompose complex fractions into smaller terms, either if we saw that the complex fraction was improper, that is, the highest exponent in the numerator is equal to or greater than the highest exponent in the denominator, or if it was proper, if the denominator was able to be decomposed into distinct linear factors. Today we're going to cover alternative cases of these proper rational functions. For this one, we have non-distinct linear factors. So what does that mean? If we take that denominator and we factor it out, we get that x minus 1 and x minus 1. And these are non-distinct linear factors because, well, they're non-distinct. They're the exact same linear factor. And if we were to try it out the same strategy that I covered in the last video with distinct linear factors, you're going to find out that this isn't going to work. Why? Because, well, you're not going to be able to cancel out one of them and find the other. So how are we going to deal with this dilemma? Well, when you have non-distinct linear factors, what you do is that for each of those factors, there's still going to be one of the a and b terms, but for each successive non-distinct factor, you're going to increase the exponent by 1. So what does that look like when we decompose? We take the first x minus 1 and we put it in the denominator of the a term. And then for the second x minus 1, we still put in the denominator of the b term, but now we increase its exponent to 2. Because if you think about it, the first x minus 1 term, right here, this is to the power of 1. But anything that's to the power of 1 is just by itself, so we don't really need to include that. Now let's say if there was another x minus 1 term in here, then we would have a plus c term, and then we'd have x minus 1 to the third power. So I think you get the point. But let's stick to what we have right now. So this is how you decompose it with partial fractions. A over x minus 1 and b over x minus 1 squared. And then what you do from here, of course, is try to cancel out the denominators so that what you're left with is just the numerator of the original rational function. So we're going to have to multiply everything by 2x minus 1s in order to do that. So if we multiply this by x minus 1 and x minus 1, well, these cancel out. If we were to do that for the a term, only one of the x minus 1s would cancel out, and you're left with a times x minus 1. But for the b term, what's really nice about this one, because it's over x minus 1 squared, these both collectively cancel out. So when you do that, what you're left with is a times x minus 1 plus b by itself, all equal to 2x plus 4. So now the strategy here is familiar. What you do is substitute in values of x so that you can isolate either a or b. So let's start with substituting in 1, because when x is equal to 1, this would turn into 0, canceling out that a. So we do that, and we just get that b is equal to 6, because we're also substituting the 1 in here, and 2 plus 4 is 6. So how would we be able to find the a term if there's no way to cancel out the b term, since it's by itself? Well, we already know what the b term is. It's 6. So you can actually just substitute in 6 for b, while substituting a random value of x other than 1 to find a. So let's say that x is equal to 0. So we substitute in 0 for each x, and we also substitute in 6 for b. And when we do that, we get that negative a plus 6 is equal to 4. And then from there, we could easily find that a is equal to 2. So again, we put in the a and b values that we found back into those partial fractions, and we get that 2 over x minus 1 plus 6 over x minus 1 squared is equivalent to the original rational function. And as always, if this was an integration problem, then solving with partial fractions makes it much easier for us to find the antiderivative of this function. So 2 over x minus 1, that's just 2 ln of x minus 1. And then 6 over x minus 1 squared. You could use u sub here because it's a more complex sum fraction. but x minus 1, the derivative of that is just 1. So really what you're dealing with is simple stuff. So 2 ln of x minus 1 minus 6 over x minus 1. And if you want an explanation for how that turned into that, again, u is equal to x minus 1, and du is just 1 dx. So what you're really dealing with here is just 6 over u squared, which is just 6u negative 2. So this increases by 1, so this turns into negative 1 times 6 is negative 6 times u to the negative first power, which is just x minus 1, so negative 6 over x minus 1, and then plus c. So pretty easy example. Let's go on to a harder example of non-distinct linear factors. Here we have example 2. This one's a little harder. Why? Because look at that denominator. We got an x cubed in there, and well, that's never a good thing. So as always, let's factor out the denominator. So our first step, we can factor out x squared, and then we're left with x squared times x minus 1. But are we really done here? Well, yes. But is this a linear factor? Well, x squared is a quadratic factor. But let's think about this. What is x squared equal to? It's just x times x. Two linear factors multiplied together equal to x squared. So actually, yes, this is all linear factors. But what that also means is that what we're dealing with here are two x's. So when we split it up, we're again going to have to apply the principle of the non-distinct linear factor partial fraction decomposition. So for every successive x term, you add the exponent by 1, starting with 1. So again, say this was x to the first power. The second x would become x to the second power. And then I started with a over x minus 1 so that, it's easier to see. But yes, this would be the process of splitting it up. And then again, what you do is you cancel out all the terms so that you're just left with the numerator of the original function. So multiply everything by x squared and x minus 1. So these cancel out. X squared in this case cancels out, and then you have x minus 1. You have x squared, and then x minus 1. The x minus 1 cancels out. Now b is a little tricky because you have x squared and then x minus 1. Only one of the x's can cancel out in this case, which is unfortunate. But what that means, what you're left with in the end, is ax squared plus bx times x minus 1 plus c times x minus 1 equals 7x minus 1. So clearly, we have a little complicated equation here. So how are we going to start this? Well, you should immediately be able to realize that if you substitute in 0 for x, we can cancel out a and b because they're both being multiplied by some form of x, and we're left with the c. So let's start with x equals 0, substitute in 0 for each x, and we're left with negative c is equal to negative 1, or c is equal to 1. You may also notice that if we substitute in 1, we cancel out the x minus 1 term, which the b and the c values have. So 1 minus 1 is equal to 0. So if we substitute in 1, we can cancel out the b and c and solve for a, and a is just equal to 6 if you compute all of this math here. So now we got to find the b term, but how are we going to do that? B is attached to both an x and an x minus 1. So what we're going to have to do, like the last example, is substitute in a random value of x while also substituting in one or more of these a and c values. So let's say let x is equal to negative 1. That's not going to cancel anything out, but we can substitute in the a and c values because we know what they are. So if we were to do that, we get, again, this complicated expression. And if we were to simplify it down, we get 6 plus 2b minus 2 is equal to negative 8. So now we can just solve for b. 2b is equal to negative 12, or b is equal to negative 6. Alternatively, something you could have done is solve for a system of equations if you were stuck finding two of the values. But I don't really recommend it because I think it's just way too much work. If you already solved for one or two of the values and you already know what it is, why don't you just use them to, solve for the rest? I mean, it doesn't really make sense. Anyway, our final answer, when we decompose this into partial fractions, is 6 over x minus 1 plus negative 6 over x plus 1 over x squared. Now, why did I leave this minus in the numerator and not just put it here? I don't know. I did it because I think that when integrating it, it just makes more sense. Because after all, these two fractions are in, that form where, it's just ln. So if you find the integral of these terms, it's just 6 ln of x minus 1. And then this becomes 6 ln of x, or negative 6 ln of x. Again, this is just x to the negative second power. So what is the antiderivative of that? Well, it just turns into this, negative 1 over x. And then don't forget the plus c at the end. Finally, we have irreducible quadratic factor. So this is the final case that we're going to cover today. And this is when you have a quadratic factor that you cannot simplify. So we had that in the last example. We had x squared, but that one is reducible. You can just reduce x squared into 2x's. So let us do this one. Simplify the denominator into x times x squared plus 1. And x squared plus 1, no matter what you do, you can't simplify that. So we don't have a linear factor in this case, but we do have a quadratic factor. So how are we going to split this up when we have a quadratic factor? Well, if you noticed the format for all the previous examples where we use linear factors, we had, multiple terms, and in the numerator, we had a constant in it. No matter what value we found, whether it was whole number or a fraction, it was just a constant with no variable. And why is that? Because really the whole trick of partial fractions is to reduce a complex fraction into a sum of terms like the derivative. Because, well, what's the derivative of any linear function? You just get either a sum of constant or just a constant by itself. Because the derivative of just x is, well, just 1. So what's the derivative of a quadratic factor? Well, it would be a linear factor, but not just a linear factor and a constant if applicable. So that means when separating this, we have an x and an x squared plus 1. For the x squared plus 1, you have to separate it into another fraction in the form of a linear equation. So here I have bx plus c. So I split up the x, put it in a over x, and then for the x squared plus 1, I put it over the bx plus c. And then that equals 12x plus 1 over x times x squared plus 1, the original equation. So even though we only have 2 factors here, we're still essentially finding 3 values, a, b, and c. Anyway, let us get started canceling out our values. So again, we're going to get rid of the x and x squared plus 1. For each of these terms. So times x, x squared plus 1, x squared plus 1 cancels out here, and then x squared plus 1, and then times x here, the x cancels out. So what we're left with is a times x squared plus 1 plus bx plus c times x, all equal to 12x plus 1. So a little complicated, but we can make it work. So how can we get started here? Well, we can't use a negative 1 in this case because, well, if we put a negative 1 here, that's just going to equal positive 1. That's not what we need. But what we can do is substitute in 0 because that's just going to cancel out this whole portion, and we can just solve for a pretty easily. So let x equal 0, substitute in 0, get that a is just equal to 1. So how are we going to find b and c? Well, we have a problem because if you check here, we can't really cancel out b and c with any value other than 0, and 0 cancels both of them out. But we need to find what each of their individual values are, so this is going to be a problem. But we do know what a is, so what we're going to have to do is substitute in, again, a random value of x, and we're going to have to get ready, make a system of equations. Man. So let's say let x is equal to 1. We do that. We get this expression, 2 plus b plus c is equal to 13, or b plus c is equal to 11. Now we're going to have to substitute in another random value of x. Let's say negative 1. We do that, and we get that b minus c is equal to negative 13. So now we have our two equations. We got to make a system of equations. And I know I made fun of people for doing this earlier in the video, but that's because they were doing it for non-distinct linear factors. I mean, why would you do that? But for here, in this case, you have to. So let's set it up, put them together. We notice immediately we can just cancel out the c's because we have a positive c and a negative c. Plus c minus c equals nothing. So if we were to add all this up, we would get that 2b is equal to negative 2. And then obviously from here, we can just find that b is equal to -1. So now that we know what b is, we can just take one of our old expressions of b and c together, whether it's b plus c is equal to 11 or b minus c is equal to -13, and find for c. This one is easier, b plus c is equal to 11. So let's use that. We substitute in -1 for b. So we get -1 plus c is equal to 11. C is just equal to 12. So now we know what all the a, b, and c terms is. So again, you just plug them in. So yes, if you were to simplify it into partial fractions, this is what it would look like. And again, if we were integrating here, this does put it in a much easier format. And you might be wondering, well, how am I going to integrate this part of the function? Well, we can split this up into two smaller fractions actually. Not using partial fractions, of course, but because the numerator is a sum or a subtraction of values, and then we can just split that up while keeping the denominator the same. So if we were to do that, we get 1 over x minus x over x squared plus 1. I just moved the negative outside. And then I have plus 12 over x squared plus 1. So if you know a constant over x squared plus 1, the antiderivative of that is just tan inverse of x. And then for this one right here, x squared plus 1, x over x squared plus 1, you can just use u sub. So u is equal to x squared plus 1, du is equal to 2x dx, and then we're going to have to divide by 2 to balance it out. So we're left with negative 1/2 u -1. So if we were to do that, we'd get that our whole antiderivative is ln of x minus half of ln of x squared plus 1 plus 12 times tan inverse of x plus c. And that concludes this example, and that also concludes this series. So hope you guys enjoyed this little mini series on partial fractions, and I'll see you guys next week.